What would you still like to go over then from tabular data? Lindsay? 6A. A particle moves along a horizontal line with a positive velocity, where v is a differentiable function of t. So the velocity itself is differentiable. The time t is measured in seconds, and the velocity is measured in centimeters per second. The velocity of the particle at selected times is given in the table below. And they give those to us. Based on the values in the table, what is the smallest number of times at which the velocity of the particle could equal 20 centimeters per second on the open interval from 0 to 12 seconds? All right, here's what I wrote. The velocity must equal 20 centimeters per second at least 2 times on this interval. V of t is differentiable, so it's also continuous. All right? All differentiable functions are continuous. All right? If they're differentiable through an interval, they're continuous on the interval. Since v of 0 is 37 and v of 2 is 17, and if you remember the name of the theorem, use it, but if you don't, then don't say the wrong one. The intermediate value theorem states there must be a value of t between 0 and 2 such that the velocity equals every single solitary number between 37 and 17. 20 is the one we want. Since v of 10 equals 17 and v of 12 equals 38, again use the intermediate value theorem to state the same thing. So all I really did was I went and I looked. Has to go through, since it's a continuous function, has to go through 20 to get there. And then not here though, right? We're never going to the other side of 20 again until we get there. Now, could it equal 20 somewhere else? Yeah, it could. It could start at 5, go up to 1,000, then come back down to 1 in those 2 seconds. I wouldn't expect it. Okay? But there we go. All right, what else? Number 3. All of 3 or part of 3? I don't understand. They're going to give it to you in such a way that you can. They're not going to mess with you and give you strange looking intervals for Riemann sums. Well, let's just look at 3 then. Okay? So 3 here. A bowl of soup is placed on the kitchen counter to cool. Let T of x represent the temperature of the soup at time x, where T is a differentiable function of x. I don't know if it's going to matter. It's continuous. The temperature of the soup at selected times is given in the table below. So it starts off at 108. It moves down to 95, which would seem reasonable if you're setting it on the counter to cool. All right. So use the data to find from the table to find the integral from 0 to 12 of capital T prime of x dx. I like this question. This is something that you need to be able to do here. Okay? So there's our data with T of x. Now, T of x is the antiderivative of T prime of x. Okay? So can't we use values of the antiderivative to come up with integrals? Definite integrals? Okay? So the integral from 0 to 12 of T prime of x dx will equal the antiderivative of T prime, which is T, evaluated for the upper limit of integration, minus the antiderivative of t prime, which is t, evaluated for the lower limit of integration. That's the fundamental theorem of calculus. So 95 minus 108, and we get a negative 13. Are you surprised that it's negative? You shouldn't be, because the temperature's decreasing, so as we accumulate the change, it ought to be negative. Okay? So the temperature decreased 13 degrees Fahrenheit on the interval from 0 to 12. And like I've warned you about before, they love messing around with the notation, don't they? So that you can't just memorize some rules, because all of a sudden they give us this chart with t, and then they ask us something about t prime. They could have given us, you know, like they could have given us a little t and called that a big T or what. I mean, they're going to mess with the notation. So, part B, use data from the table to find the average rate of change. The average rate of change uses the slope formula, y2 minus y1 over x2 minus x1. It'll never be y's and x's, will it? But it's the same idea. Over the time interval from 4 to 7. So, it's y2. All right, the value at 7 minus y1, the value at 4, over x2, 7 minus x1, 4. Again, those weren't y's and those weren't, actually they were x's. But can you do it? Okay, because if you can, those can be easy problems, can't they? All right, we good on B? All right. Explain the meaning of the integral from 1 to 12 of 1/12 the integral from 0 to 12 of t of x dx in terms of the temperature of the soup, and approximate the value of this integral expression by using a trapezoidal sum with 3 subintervals. Stop. Explain the meaning. What was this? It was how much the temperature changed in 12 seconds. So if you divide it by 12, now what is it? Yeah. Okay, the average temperature change. Okay? The integral accumulates from 0 to 12. Multiplying by 1/12 is the same thing dividing by 12. So if you've accumulated something, 12 somethings, and then you divide it by 12, isn't that the average? Okay? I mean, we have a theorem that says that 1 over b minus a times the integral from a to b of f of x dx is the average value. But even if you forget that, if you accumulate 12 somethings and divide by 12, you've found the average. Okay? So we can explain what it is. It represents the average temperature change. And then you do need to tell the time intervals. Okay? So explain the meaning in terms of the temperature of the soup. Okay, we've done that. Now they want us to approximate the value using the trapezoidal rule. Okay? So trapezoid area is 1/2 times the height times the sum of the bases. So we've got the 1/12 out in front because of that, and then everything in the bracket then is the integral from 0 to 12. They told us to make 3 subintervals. All right? 1, 2, 3. Okay? So first, approximate the integral from 0 to 4. So if it's from 0 to 4, remember how the height of the trapezoid is actually horizontal? Okay? If I graphed this, 0, 4, 108, 101, so 108, 101, obviously not to scale. That's our trapezoid. So 108 is one of the bases, 101 is the other base. So 1/2 times the height of 4, because the subinterval is 4, times the sum of the bases. Then the next one. So it's going to be from 4 to 7. That's going to be one base. That's going to be the other base. So if it's from 4 to 7, its height is 3. So 1/2 times the height of 3, one base. What's the other base? And then that. So the height's going to be from 7 to 12. So the height is 5 this time. One base is 99. One base is 95. So that approximates the average temperature for those 12 seconds, minutes, hours, days, minutes. Okay? Does that help? All right, now, there were several things in number 3 here that are likely to show up in the AP test. The average, how'd they word it? The average rate of change here in Part B. Maybe they'll ask you A. I'm not real sure about that one. That seems a little easy. All right? But the average rate of change, they'll ask you, in some way, shape, form, or fashion, you'll have to be able to find an average value. Maybe it's like this, where they basically give it to you and ask you if you know what it is. And then estimating a definite integral from a table. Maybe they'll tell you to use trapezoids. Maybe they'll tell you to use rectangles with a left Riemann sum. Maybe they'll say a right Riemann sum. Maybe they won't tell you. And then you approximate it, and then, but that'll be on there in some shape, guaranteed. Anything else on this worksheet we need to talk about? 4A. All right, so this time we have a table. The rate at which water is being pumped into a tank is given by the continuous increasing function R of T. All right, R of T is a rate at which water is being pumped. So it's a rate. That means it's a derivative, doesn't it? So it'll have an antiderivative. I don't even know if they ask us that. That's the stuff that kind of ought to be running through your mind, okay? A table of selected values from 0 to 20. Use a right Riemann sum. Okay, good. This follows up our number 3 then, doesn't it? Use a right Riemann sum with 4 subintervals to approximate the value of the integral from 0 to 20. All right, now, so let's see here. If I do 1, 2, 3, 4. They usually make it. It may not always be going by ones. You may have to like skip one and instead of the 0 and the 4, it might be 0 to 9, 9 to 20, and then they give you 2 more columns. It might be like that, okay? But they will give it to you in such a way that you can handle the interval. All right. So let's add those up. A right Riemann sum means to use the right edge of the rectangle as its height. So this first one, from 0 to 4, let's see, that interval is 4. So the base of that rectangle is 4. Use the right edge of the rectangle as the height. So 28 is the height. Then for the next one, from 4 to 9. From 4 to 9 is 5. So the base of that rectangle is 5. Use the right edge of the rectangle as the height. 33. Then from 9 to 17. Well, from 9 to 17 is 8. So the base of the rectangle is 8. Use the right edge of the rectangle as the height. That's 42. And then from 17 to 20 gives you a base of 3. Using the right edge of the rectangle as the height. 46. Punch it in. Okay? Now, is your approximation greater or less than the true value? All right. It's going to be greater because our function is increasing in the whole time, isn't it? 28 is bigger than 25, 33 is bigger than 28, 42 is bigger than 33, 46. So, your graph, it's not linear, but it looks like that. So if I draw a rectangle in, isn't the right edge taller than the left edge? And you can just go a rectangle at a time. The right edge is bigger between those two. 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 So we overestimated every time, didn't we? Therefore, our approximation is greater than the actual value. Okay? Anything else? Or B. A model for the rate at which water is being pumped into the tank is given by the function W of t equals 25e to the 0.03 t, where t is measured in minutes and Wt is measured in gallons per minute. Use the model to find the average rate at which water is being pumped into the tank from 0 to 20. All right. They didn't say the average rate of change of the rate, all right, because it's a rate is what they've given us. So we have to find the average of the integral from 0 to 20. You with me? Okay. So the integral from 0 to 20 gives us the amount of change from 0 to 20. Put a 1 over 20 in front of that, and that'll give you the average of whatever you're measuring from 0 to 20. Okay? And we should be able to do that on a calculator. Let me get my calculator and make sure we can. All right, so I want turn it on. It's amazing how that helps. Okay, I want the integral from 0 to 20 of this. So I need y1 to be 25 e to the 0.03 t, so x for us. So that's what I need to graph. And I need to make my window bigger. I need to be able to go from 0 to 25. I don't remember if the y values matter or not. And I don't even care if it shows up as long as it lets me take the integral. Let's see if it does. So second calc, choose the integral, lower limit 0, upper limit 20. So I get that, and I divide it by 20. Okay? And I know there are keystrokes you can use so that you don't have to graph it. There's always a comma somewhere. I never figure it out. That's the way I do it. Okay? If you can figure out the keystrokes to avoid that and not forget them, okay, fine. I did that for my function so that I could take its integral. You could go ahead and divide it by 20 if you want to before you integrate it, can't you? Because factoring a constant out is what we're doing. The constant's just already there. So I graphed that, took the integral from 0 to 25. It gave me what the integral from 0 to 25 is. Uh-oh, I did something wrong. The integral from 0 to 20, and then I divided it by 20 to get my answer. All right? Okay, I think we'll stop there.